any questions? Because the last thing we had was the tutorial on Friday. Yeah? Oops. So, here. So this is what I want to look at today. In the first class, efficiency. Okay. Now, this first lesson is easy, okay? Last week we talked about conservation of energy. Do you remember what this means? Yeah? What's conservation of energy? Louise, do you remember this? Conservation of energy, what does it mean?
And the meaning is...
Yeah? You need to check? No? Yes?
I love the energy.
About energy. Yeah, what about the energy? Yeah?
It's about energy.
Yeah, I know about energy. What about the energy?
Energy
Yeah.
can get the forces.
Oh no, you're thinking of something else. No, not this. Abraham, do you remember?
Yeah, energy doesn't get stuck or it just changes the form.
So conservation of energy means you can't make or destroy energy. You just change the energy from kinetic, potential, electrical. You just change the energy. You don't make it. Change energy, yeah?
Except the chair. The last time, yes, the energy as well.
The chair? On box. Yeah. This is the example I did, yeah. So the energy comes from somewhere, okay? But sometimes, when you have a machine, not all the energy goes into the job you want to do. So for example, if we think of we think about the light bulb, which we have here. Yeah. So just, okay, it's a light bulb, deal with it. So we have our light bulb. And into the light would go maybe 100 watts. So out comes the light. And you might think we get 100 watts, but we don't get 100 watts of light. The reason for that is because some of the energy changes into light, and then some of the energy turns into heat. And this is not what we want. For a 100 watt light bulb, how much do you think will be light, and how much do you think will be heat? Give me some numbers. What do you think light would be?
70.
Maybe 70 watts and 30 watts, yeah? 70 and 30. Anyone else got other ideas?
I think the temperature is
Yeah?
higher than 50.
So you would say, how many watts for each? What do you think? So you think more than 50? So what, like 60-40? What do you think? Your opinion. It's only your opinion. Anyone else want to? You said 70-30.
Yeah.
70 for light.
No.
Oh, 70 for heat.
Yeah.
Okay. Anyone else?
I think it's the same.
You think it's about this? Yeah? You think about maybe 3/4 is for heat and 1/4 is for light. Okay, well this is what it is more likely. It is 199. Yeah, so when you put 100 watts in, you only get 1 watt as light, and you get 99 watts as heat. So this might be surprising. And this is what we mean by efficiency. It's how much we get for what we put in. So in this example, the efficiency is quite bad. In fact, you only get 1% for your 100 that goes in. And there's a formula for this. We say the efficiency, that's this symbol here, this is the efficiency symbol, is the energy you get out, and I should point out it's the energy that you want, like the light, over the energy you get in, multiplied 100%. So in this example, it will be 1 over 100 multiply 100%, so that is 1%. It's very, very bad efficiency, very bad efficiency. Since we're talking about efficiency, can you give me some examples you feel are also badly efficient, not very efficient? So, a light bulb, not so efficient. Can you think of anything else? What else? Now, let me give you a little clue. Why is my light bulb so badly efficient? What's the reason? Well, because most of it is going to heat. So think of things at home that get hot and you don't want them to get hot. So your laptop, it gets hot. This is wasted energy. What else?
Television.
Television, a little bit, yeah, true. Anything else? Anything else?
Most electrical appliances. All electrical appliances which you don't want to get.
Yeah, so give me an example.
That's
The car engine.
Car engine, yeah.
and the phone.
Phone, yeah. So I'll give you some, okay? So a light bulb is about 1%. Okay? A vacuum cleaner? Oh, I don't know. Maybe that's about 50%. A car. What do you think a car is? Car. Yeah, what do you think it is? About 40%. 40%. Because you know the front of the car, the engine, gets hot, doesn't it? Now let's talk about the opposite. Can you think of something that maybe is near 100%? Efficiency. Yeah. I think we can do better than an oven. An oven would be good. I think we can do better. Anything else?
So it's not too electrical.
No, I suppose not. I'll tell you. An electric heater. Because if the energy is converted into heat, then that's what you want. But it's not 100% efficient. Okay? It's maybe 99.999%. There is still some energy lost with the electric heater. Any ideas what that form of energy is? The energy that is lost in the electric heater? Sound? Yes, it's sound. So you think about an electric heater, you hear it, don't you? Maybe sort of buzzing, like a little sound? Yeah? Well, that's okay. You know an electric heater, when you switch the heater on, you hear a buzzing sound, don't you? That's not what you want.
Air conditioner.
Air conditioner's pretty good. It's pretty efficient, yeah?
Isn't like a bathroom off there?
Yes, but that's not because of inefficiency. That's moving the heat from the room out back, so it's not caused by the motor. It's pretty good. Your fridge is also pretty good. Fridges, okay? So anyways, what causes inefficiency? Well, the main reason is heat loss. Okay, so we need to make note for that in the exam. In the exam, they would say, why is this not 100% efficient? And the answer is, energy is always lost through heat. There's always heat loss, like with the car, the TV, all this stuff. So, we'll say, where's it gone? Efficiency can never equal 100%. Some energy is lost always. Sorry, that's not a good sentence, I know. Some energy is lost always. Most lost energy is in the form of heat. So do you remember when you did your collisions, the car and the truck hit each other, and you calculate the kinetic energy? You remember that? Was the kinetic energy after the collision bigger or smaller than before the collision? Smaller. This lost energy was changed into heat when the two crash. They are warmer after the crash. Okay? Now if I go back to the formula for a moment, well actually I'll go up here. What I can do here is I can also divide the top and the bottom by T. What is energy divided by time? I gave you that formula last week. Energy divided by time is power. So you have two ways to write the formula, okay? You can write it like this. Efficiency is energy out over energy in times 100%, or you can say efficiency is power out over power in multiply 100. So either will work. Let's have a look at an example. Okay. So for example, can I go down? Yeah. You all have phones, of course, and you notice when you charge up your phone, iPhone, and here's the plug here. This plug, the energy that goes into it, we'll say is 4.83 joules per second, and then the energy travels, and it goes into charging up the battery. Now, 1.31 joules goes into the battery, and then what happens is the rest, the 4.83 minus 1.31, that leaves as heat. You know when you charge your phone up, the battery feels warm. Yeah. You don't want this, okay, because that's inefficient. So let's calculate the efficiency here. So efficiency, what's the energy I want? The energy I get out? It's this. This is what I want, isn't it? How much energy do I put in? Sorry, these are joules per second. Joules per second. How much energy goes in? 4.83. Multiply 100. Okay, can you use your calculator? Tell me what you get, please.
$27.1.
27.1%. What do you think? Good or bad? It's kind of bad, isn't it? It's not great. Really, you want more than 90% good efficiency. So you see, these questions are really, really easy to do. And how long did it take me to do this? Like 1 minute? Yeah. So let me give you 5 questions to do now. I'll give you 5 minutes and then we'll go on to the next lesson, okay? So it's not even a full lesson. It's not even half a lesson. It's like a quarter of a lesson.